Welcome to Robotics at the Cutting Edge, a special episode of AI Frontiers. Today, we explore breakthroughs from 21 new research papers in the cs.RO category, published on September 4th, 2025. Discover how robots are learning, sensing, planning, and adapting with unprecedented sophistication. Whether you are an expert, enthusiast, or simply curious about intelligent machines, this episode offers deep insights, culminating in our featured paper of the day from Posadas-Nava and colleagues. Join us as we chart the trajectory of intelligent robotics innovation. Imagine teaching a robot to dock with the International Space Station using just 100 human demonstrations, less than the number of times most people tie their shoes in a year. This robot not only matched, but outperformed traditional algorithms trained on 40 million simulated attempts. It's like mastering the piano by watching a virtuoso just a handful of times, rather than practicing for years. Robotics is now redefining what's possible with limited data, hinting at a revolution in sample efficiency. Are we witnessing the dawn of a new era where fewer demonstrations can yield greater impact? Robotics research is shaping the world around us, from factories and homes to hospitals and space missions. The latest cs.RO papers on the arXiv preprint server introduce transformative ideas and bold experiments that are driving the field forward. In this episode, key research themes will be decoded and transformative findings highlighted. Listeners will meet the minds behind these innovations and learn about the methods empowering robots to become smarter, faster, and more adaptive. The journey reveals not just technological progress, but the expanding potential of intelligent machines. Robotics is best understood as a symphony of ideas, where perception, control, planning, and learning each play distinct roles in harmony. The cs.RO category on the arXiv preprint server serves as a nexus, bringing together computer science, artificial intelligence, and engineering disciplines. No longer confined to factory floors, robots are emerging as real-world collaborators. Every research paper contributes a unique note to this evolving melody, illustrating the field's dynamic and multidisciplinary nature. A central theme in recent robotics research is learning from demonstration and reinforcement learning. This process is analogous to how children learn to ride a bicycle, by watching, wobbling, and gradually achieving balance. Zhang and colleagues demonstrated that even suboptimal, rule-based demonstrations can effectively bootstrap robot learning, reducing reliance on expert data and accelerating autonomy. Shen's research further advanced this by combining demonstration data with efficient exploration, enhancing learning speed and safety. Reinforcement learning, where robots improve through trial and reward, remains a cornerstone of these advancements. Multimodal perception and sensor fusion are equipping robots with multisensory capabilities, similar to a baker relying on sight, touch, and even guidance. Kansana's Surformer V2 model fuses visual and tactile data using a late fusion technique, allowing each sensory stream to specialize before combining their strengths. This results in superior surface classification, particularly in noisy environments. Hue's OVGrasp system integrates vision, language, and voice commands, enabling adaptive and real-time robotic control. Sensor fusion, combining multiple data streams, empowers robots to make robust decisions in the real world. Planning, adaptation, and scalability are critical for robots operating in complex, dynamic environments. Saha and colleagues introduced planning directly from point cloud data, enabling robots to rearrange objects in cluttered settings without predefined rules. Posadas-Nava's team utilized transformer models to chunk sequences of actions, greatly improving efficiency in tasks like spacecraft docking. Use diffusion-based frameworks facilitate skill transfer across simulation and real environments, while Zoo's EMMA system scales learning using egocentric human data. Robots are increasingly capable city explorers, adept at navigating dynamic and unpredictable environments. The latest research brings to light several key findings. Posadas-Nava and colleagues showed that 100 expert demonstrations can match the effectiveness of 40 million reinforcement learning trials for docking with the ISS. Kansana's late fusion approach in Surformer v2 significantly enhances robot surface classification. Zoo's EMA framework enables scalable, data-driven learning by utilizing extensive human demonstration data. GIA's InGrid platform allows AI to automatically design innovative robot mechanisms, broadening access to advanced robotics. Whose OVGrasp exemplifies real-time, adaptive assistive robotics, merging multiple sensory modalities for improved user support. Today's featured paper, Action Chunking with Transformers for Image-Based Spacecraft Guidance and Control by Posadas-Nava et al., tackles the formidable challenge of teaching robots to dock with the International Space Station using minimal demonstrations. While traditional reinforcement learning requires millions of simulated runs, an approach both costly and risky, the ACT method segments control into meaningful action chunks. Transformer models are then employed to capture temporal patterns within these sequences. Remarkably, only 100 expert demonstrations, totaling 6,300 interactions, were used to achieve superior performance. The core of the ACT method lies in how it revolutionizes the mapping from observation to action. Instead of creating a direct link between each observation and a control command, ACT groups actions into coherent sequences or chunks, analogous to phrases in a sentence. This allows a transformer model proficient in temporal sequence learning to internalize complex behaviors more efficiently. The approach mirrors human learning, where mastering sequences takes precedence over micromanaging every step. Notably, this technique outperforms conventional baselines trained with massively larger datasets. The implications of ACT extend well beyond the domain of space robotics. By dramatically improving sample efficiency, the method enables robots to learn more from less data, yielding smoother and safer trajectories, an essential feature in high-stakes environments. The underlying approach can be generalized to autonomous vehicles, manufacturing, and even domestic settings, inspired by how pilots and astronauts master complex tasks by internalizing action sequences. This advance points toward a future in which robots learn from fewer but richer examples, advancing both safety and capability. The future of robotics resembles a rapidly growing forest, with new branches extending in multiple directions. Advances in sample-efficient learning are reducing the barrier of data scarcity. Sensofusion and domain adaptation are unlocking new robotic abilities, while AI-driven mechanism design is enabling the creation of custom robots. This trajectory suggests a hopeful analogy. Robots are beginning to grow new skills and even new physical forms, expanding the boundaries of what is possible through intelligent adaptation and design. In conclusion, the pace of robotic evolution is accelerating, transitioning from demonstrations to real-world dexterity. The work of Posadas-Nava and colleagues exemplifies the power of learning from limited data. Contributions from researchers such as Kansana, Zoo, Ja, and Hu are driving progress in perception, scalability, and design. Listeners are encouraged to explore these papers, participate in the ongoing discussion, and imagine new possibilities for the field. The future of robotics is open to all. What role will you play in shaping it? This presentation was synthesized using GPT 4.1 by OpenAI for summarization and narrative construction. The text-to-speech component was provided by OpenAI, with visuals guided by Google image generation tools. A human expert carefully reviewed all synthesized content to ensure clarity and accuracy, though minor oversights may remain. Full references are provided for transparency. The synthesis process combines the speed and breadth of artificial intelligence with expert human insight to deliver reliable research overviews. Subscribe to AI Frontiers for the latest in robotics and artificial intelligence. Receive research breakdowns, expert interviews, and more by joining our channel, AI Frontiers. Unlock tomorrow's breakthroughs and become part of our growing community. Your curiosity drives the next generation of intelligent machines. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.